Well, hello, chemistry students. I pray you guys are all doing okay as we're all kind of being held to our homes for a little while. Pray your families are doing okay, and we're going to do our very best to try to continue our study of the subject of chemistry. My plan over the next few weeks through these video lectures and PowerPoint annotations is to look at chapter 16 this week, some sections of chapter 18 next week, and then 19 and 20 we're going to do some selections from both of those. We'll take a couple of tests over the next few weeks, and then you'll just have the final and we'll be done with the class. So we just have a few weeks left, and some of the stuff that we're going to be looking at doesn't have a whole lot of math to it. There's just a little bit of algebra, a little bit of logarithmic stuff we'll talk about today, but I'll show you how to just talk about doing that on your calculator. And it's going to be a lot of descriptive chemistry and stuff. So I hope you enjoy these last few chapters. Sorry I don't get to actually be with you guys, and so this is the next best thing of being able to be in class together. And let me know if you guys have any questions or comments regarding these videos. If there's ways I can improve them, please let me know. Or if there's ways I can answer any questions you guys have, I would love to help you any way that I can. So keep all of that in mind. Here we are, chapter 16. Be looking at acids, bases, and salts together in this chapter. Section A, we're going to be defining acids and bases. So let's first of all talk about the properties of acids. Normally, acids have a sour taste to them. They are electrolytes. I think I spelled that wrong in the slide, sorry. Electrolytes, which means that they release ions and they conduct electricity when dissolved in water. And they react with litmus paper in the following way, turning blue litmus paper red. They react with active metals above the hydrogen ion on the activity series. An example is magnesium and hydrochloric acid. And this is something I would love to show you in class, but just a little beaker of hydrochloric acid, and you put a bit of magnesium ribbon into it, and it's a vigorous reaction which releases hydrogen gas. You can test for that hydrogen gas by getting a little pop if you bring a glowing stick inside of that. So anyway, magnesium and hydrochloric acid is a great example of this. It will react strongly with magnesium. So magnesium plus hydrochloric acid looks kind of like this. You get magnesium 2 ions aqueous as a result of it, along with some chlorine ions aqueous. You get hydrogen gas that comes off of that reaction. Now, base properties. Bases are bitter to the taste. They are slippery in nature. They react with litmus paper, turning red litmus paper blue. Now, when you bring acids and bases together, you get what's called a neutralization reaction. So when an acid and base neutralize each other in an aqueous solution to produce water and a salt. A great example of this is hydrochloric acid and sodium hydroxide. For the HCl, aqueous, dissolved in water, plus sodium hydroxide, again, dissolved in water, yields NaCl, something you guys are very familiar with, sodium chloride, or otherwise known as table salt, and water, H2O. So note here what happens. The hydrogen from HCl and the hydroxide group from NaOH makes HOH, otherwise known as H2O, water. And what's left is the sodium and the chlorine, which forms sodium chloride. This is what we would call excuse my writing with this crazy mouse, this is called a double replacement. Now I'm committed, I got to finish it. Replacement reaction. So it's a double replacement reaction. So HCl plus NaOH yields NaCl plus water. So these neutralization reactions always yield some sort of salt. And by salt, we mean the stuff that's left over when the hydrogen and the hydroxide groups are removed, and then water, which is the hydrogen plus the hydroxide. So here's some common acids and bases. So vinegar is something you're familiar with by name. It's actually acetic acid, HC2H3O2. Vitamins like vitamin C is absorbic acid, C6H6O6. Soft drinks have carbonic acid in them. Citrus fruit has citric acid. Bee venom, also known as formic acid. Sour milk and sour mussels both have lactic acid in them. Rhubarb has oxalic acid. Household ammonia is usually ammonium hydroxide, NH4OH. Battery acid is sulfuric acid. Lime is calcium hydroxide. Milk of magnesia is magnesium hydroxide. Lye is sodium hydroxide. So those are also just some examples of various acids and bases, and the common names that we know them by, but the actual chemical formulas that are behind them. Now, there are several different types of definitions for acids and bases, and we're going to talk about them in turn. So first, the Arrhenius definition is that acids give a hydrogen plus ion or a proton when in water. For example is sulfuric acid. Note here this H2, this will provide an H plus, will give you 2 of those H plus ions when dissolved in water. So acids give an H plus ion when in water, whereas bases give a hydroxide ion, that OH negative ion, when in water. So again, if we had something like barium hydroxide, when this goes into water, you get a barium 2 plus ion, and then you'll get an OH minus ion, but you'll get, remember, 2 of them out of this because of this subscript 2. So by definition, by Arrhenius's definition, acids give an H plus ion, whereas bases give an OH negative ion. Now consider this. Not every substance having H's or OH's is an acid or a base. Here we have CH4 and CH3OH. Here's a hydrogen. Here's a hydroxide group, but neither of these are either acids or bases. So what about the Brønsted-Lowry definition? He defined acids as that which donate a proton, which is the exact same definition as Arrhenius. However, when he got to bases, he said bases are materials that accept the proton, which is a much wider definition than Arrhenius. Remember, Arrhenius said that a base is defined by donating a hydroxide group. Here, he's saying that a base is just anything that will accept a proton, whereas acids are that which will donate the proton. So each Brønsted-Lowry acid can lose an H+, and if conditions were correct, the resulting ion could gain the proton back. Thus, the ion is called a conjugate base of the acid since it accepts the proton. So if we had HCl, for example, and it was in water, it could dissociate into H plus Cl minus. But that means if conditions are right, these also could run in reverse, and the chlorine minus here could pick up an H plus and form HCl, which means running in the opposite direction, running this way, chlorine minus ion could be referred to as a conjugate base because it could accept the proton if running in the opposite direction. So here, an acid forms here a conjugate base, which could make it back into an acid under the right conditions. So each Brønsted-Lowry base can gain an H+, and if conditions are correct, the resulting ion could lose the proton. This ion is called the conjugate acid of the base since it donates a proton. So here is an example of HF plus H2O yielding H3O plus and F minus. So note here is an acid able to give a proton in the form of this H to this side. But if we run this reaction in the opposite direction, this fluorine is able to receive a hydrogen ion moving back this direction. So it's a conjugate base. In this case, this is the base on this side because it's able to receive a hydrogen plus, but going this direction, the H3O plus would give up the hydrogen ion, which means that it's a conjugate acid. So note that every acid has a conjugate base, and every base has a conjugate acid. So acids donate protons called deprotonation. These protons join a water molecule forming H3O plus, a hydronium ion. Bases accept protons called protonation. So how does Arrhenius differ from Brønsted-Lowry? They don't differ, remember, on the acid definition. They're the same there. Where they differ is on the definition of the base. What is Brønsted-Lowry's base in this reaction? So we have here HSO4 minus plus HCl yielding H2SO4 plus Cl minus. So you have to ask yourself the question, remember, a Brønsted-Lowry base is that which receives a proton, receives a hydrogen ion, almost always in general. So receives the hydrogen. So what from this side receives a hydrogen going this way? Well, note here that this is HSO4 minus, and it becomes H2SO4. So here in this case, the thing that is the base is this HSO4 minus because it receives a hydrogen ion moving from the left to the right. Now, Lewis defined acids a little bit different, acids and bases differently. He said that acids are those things which accept a pair of electrons or one empty orbital, whereas bases donate a pair of electrons. So instead of looking at it from the positive side of things, he looked at it from the negative side, looking towards the electrons. An example is given to you here down at the bottom of this slide. So we have NH3, and note here at the top of this, we have just a pair of electrons. And it's being NH3 here added with H2O, just water, which you'll note here is 2 hydrogen ions combined with oxygen. When we come to this side, it becomes NH4+. So this hydrogen is taken on to the NH3, making it NH4+. But another way of looking at it is it's that the pair of electrons from NH3 are donated to the H2O, and H2O receives that pair of electrons, making it OH minus. And so another way of just looking at this is by looking who accepts a pair of electrons and who donates the pair of electrons. So bases are those that donate a pair of electrons, and acids are the ones which accept a pair of electrons. So what is true about acids? What do you think about this? That's right, they turn litmus paper red. Now, acid-base model summary looks like this. Arrhenius and Brønsted-Lowry, remember, have the same definition when it comes to acids. They just differ on their definition for a base. Lewis is the one that talks about electron pairs rather than protons. But otherwise, you see that these definitions are very similar to one another. Okay, so let's talk about 16b now, about acid-base equilibria. So we begin by discussing the self-ionization of water. Water ionizes into H plus and OH minus ions. It self-ionizes. So H2O, through a reversible reaction, can form H plus and OH minus ions. Now, but this is it is also the case that these hydrogen ions that are found will combine with other water molecules that are there, forming H3O plus ions. So the summary reaction looks like this. A water molecule plus a water molecule yields an H3O plus an OH minus. So an H from here is donated here, and this one's left with OH minus, and this is comes up to the hydronium ion, H3O plus. So we have hydronium here, and we have hydroxide here. So a hydrogen ion, the hydroxide ion, and the hydronium ion. Now, what do acids release? Remember from our previous discussion? That's right, they release protons. What is formed by the protons that are released by acids? Remember, when that H plus is sitting there, what does it then combine with? It combines with water molecules forming hydroniums, right? This is where we get an H plus the H2O yielding H3O plus. Okay, that's the hydronium ion. All right, so in these reactions, there is an ionization constant, which we know as Kw, K little w. And that is equal to the concentration of hydronium ions here times the concentration of hydroxide ions. And it always equals the same constant. And there's a constant for water at a certain temperature. So the constant for water at 25 degrees Celsius, if the temperature changes, this constant changes. But at 25 degrees Celsius, which we know is standard temperature. It's 1.0 times 10 to the negative 14. This is the constant of ionization for water. This is a number you should memorize. Okay, there's not many that I have you memorize. You should remember this one. 1 times 10 to the negative 14. This dot just means the same thing as a multiply, right? So if you like the x instead, that's fine. But so 1.0 times 10 to the negative 14 is the constant. And this amount does change at different temperatures. So the concentration of hydronium ions times the concentration of hydroxide ions always equals 1 times 10 to the negative 14. So this means, if you remember the law of how you multiply exponents, all we have to do, if these bases are the same, all we have to do is when we multiply them together, we add the exponents. So if the hydronium ion concentration is 10 to the minus 10, and we know that the total over here has to be 10 to the minus 14, we know the hydroxide ion concentration must be 10 to the minus 4. Because all you do in a multiplication with the same base is you just add these exponents. So negative 10 plus a negative 4 equals a negative 14. So that's how we get this. So if instead the hydronium ion concentration is 1 times 10 to the negative third, all we do again is negative 14 has to be the total. Negative 3, we remember we're just going to here subtract a negative 3 from that to see what we would need for the other one to be, which in this case, this becomes a positive, so it would be a negative 11, right? Because negative 11 plus negative 3 yields negative 14. So that's what this should be. The hydroxide ion concentration must be negative 11. Note here, you just multiply, you add this number to get to negative 14, just like you added here. So if I made the hydronium concentration a negative 8, for example, then you just ask yourself, what do I need to add to negative 8 to get to negative 14 to get to hydroxide one? So in this case, it would be negative 6, right? Because those add together to negative 14. So we're always trying to add up to negative 14 on these concentrations. So here's a sample problem. Concentration of hydronium ions in a mild acid is found to be 5 times 10 to the negative 7. Now note here, it is 5 here, not 1. So keep that in mind. What is the concentration or molarity of hydroxide ions? So this is hydronium. This is your H3O plus. And now they're asking for the concentration of OH minus. Now remember, we have the equation that's given to us that the hydronium concentration times the hydroxide concentration has to always equal this constant for water if it's at 25 degrees C, which it is. So this is 1 times 10 to the negative 14. And we're provided with the hydronium ion concentration, so we just have to solve for that, leaving hydroxide by itself, which means if these are multiplied together, we just have to divide it to the other side, which is what we're doing down here. So hydroxide, when it's by itself, right here, would equal the Kw divided by H3O, which is what we have here. Kw divided by the H3O plus number. So we can now just put these known values in here. So we know that the Kw is 1 times 10 to the negative 14, and the number that they gave us is 5 times 10 to the 7. Now all you have to do on these is just put them into the calculator. Okay, you just put them into a scientific calculator, and you can solve all of these. So you just do one exponent. You might have to use the E key on your calculator, or if you have a graphing calculator, you can use the caret. Sometimes you have a calculator that has that, and then write in parentheses like this, and then you would divide, use the division symbol, and then 5e or caret negative 7. So either way, so you could do, if you're typing a scientific calculator, 1e negative 14 divided by 5e negative 7, and you should be able to get the answer of 2 times 10 to the negative 8 molar. All right, so since Kw is 1 times 10 to the negative 14, and these multiplied together have to equal that, each water molecule self-ionizes into one H3O plus and or a OH minus. And then H3O concentration must equal the OH concentration. Therefore, when everything is balanced, when the pH level is balanced, when they're neutral, they're both going to be 1 times 10 to the negative 7. That means 1 out of about 555 million water molecules are ionized at any given instant. So 1 out of about 555 million. So see, these percentages are very, very small. Now, pH stands for the power of the hydronium ion. So pH is the negative logarithm of the hydronium ion concentration by definition. pH is this equation, the negative log of H3O plus concentration. By the way, if I didn't already mention this, these square brackets just mean concentration. That's what that means. Concentration of H3O plus, hydronium ion. So the concentration of hydronium ions, you take the negative log of that to get the pH value. And we're going to do just a couple examples. Again, you're just going to punch this in the calculator and hit the negative log of whatever the number is, and you get the. So, for example, if I tell you that again, this is the hydronium ion concentration is 1 times 10 to the negative 7. You put that into a calculator. You take the log of 1 e or 1 caret to negative 7, or caret. I'm sorry, 1 times 10 caret negative 7, and then you take the log of that number, and then you take the negative of it. You'll get 7. All right. Or here, if you do the same thing with this number, again, it's negative log of 1, and then you'll times 10, and then you write your caret or your e, depending on which one you have on your calculator, negative 7. You'll get this answer, 7. And if you put 8 there, you would get 8. Or if it was 4 there, you'd get 4. So it's just the opposite sign of whatever is on the 10. If this number is a 1, then these are really quick problems to solve. If I ask you for the pH of 1 times 10 to the negative 7, you tell me 7. If it's 1 times 10 to the negative 8, you tell me 8. If it's 1 times 10 to the negative 4, you tell me 4. If it's 1 times 10 to the negative 2, you tell me 2. If I said 1 times 10 to the negative 12, you tell me 12. So those are very, very simple if this base is 1. You don't even need a calculator for any of that. But if this number happens to not be 1, then you would just put it into the calculator like this, and it will give you the value. A pH of 7 means that the solution is neutral. A pH of anything from 0 to 7 is acidic, and anything of 7 to 14 is basic. So the closer it is to 0, the more acidic it is. The closer to 14 it is, the more basic it is. So here's your scale. It's neutral at 7, acid lower than 7. It's a base when it's higher than 7. Now, some of you have done things of this nature. If you have a pool at your house, you had to take pH levels of that. You've had little test strips before. This is what you're measuring when you're doing that. So here's a concentration of hydronium ions in shampoo being 2 times 10 to the negative 5. What's the pH of this shampoo? I'm going to put that into the calculator. We'll do negative log of the concentration, or negative log of 2 times 10 to the negative 5th. And you'll get an answer of negative 4.7. Negative times a negative just becomes a positive. So the pH is 4.7 of that shampoo. Example here, if pH is 7, then we know what the concentration of hydronium ion, we can go work it backwards. It's just 1 times 10 to the negative 7. And if the Kw for water is 1 times 10 to the negative 14, then we know the hydronium hydroxide concentration must be the exact same thing. Remember, if it's at neutral, they're both going to be 1 times 10 to the negative 7, because we would just add these two exponents, negative 7 plus negative 7 yields negative 14. And that's that number that they all add to here for the Kw. If pH is 2, then again, we would just say that that 2 becomes a negative on this 1 times 10 to the negative 2. And if we wanted to solve for the hydroxide concentration, we just say what added to that gets us to negative 14. In this case, it'd be negative 12. Negative 12 times plus negative 2 yields negative 14. So these problems shouldn't be that difficult. We're just looking at what negative numbers add up to 14, right? To negative 14. So what does the pH equal if hydronium ion equals 1 times 10 to the negative 10? Well, if we're looking for pH, here's the hydroxide, I'm sorry, not hydroxide, hydronium ion. So we just look at this number and we take the negative of it. So it's just 10, right? Just 10. Okay, now POH is just like pH, except in this case, we're looking at the hydroxide ion concentration rather than the hydronium ion. So instead of looking at H3O+, we're looking at the concentration of OH-. Example, if OH- concentration is 1 times 10 to the negative 9, POH is just, remember, the negative of this, which is just 9. So here, OH matches OH. That's what you're looking for to make sure you're giving me the right value. If OH negative is 1 times 10 to the negative 3, and we're looking for POH, we have OH, OH, they match, then we just take this number and take the negative of it, 3. So these problems are pretty easy problems. What does POH equal if OH minus equals 1 times 10 to the negative 10? Again, we just look at this number. Since this base is a 1, it's just very easy. We look at this, we take the negative of it, and we get 10. All right. And again, these always multiply the concentration, multiply together to get this to 1 times 10 to the negative 14. So pH plus POH must always equal 14, right? So these two numbers, if this is a 5, what does POH need to be? Well, it needs to add up to 14. So it's just 14 minus 5 would be 9. If pH is 6, this has to be 8. If pH is 2, this has to be 12. See how this works? These numbers always have to equal 14. So if pH is 5, then the hydronium ion concentration is 1 times 10 to the negative 5th. That means the OH concentration is 1 times 10 to the negative 9, because remember, negative 5 plus negative 9 is negative 14. And the POH must be 9, because 9 plus 5 is 14. If pH is 2, POH is 12. If pH is 10, POH is 4. These numbers always have to add up to 14. This is a little chart just showing the conversions of how you would go about going from one thing to the other. There's a chart like this in your book as well, which you can look over. Okay, sample problem 4. Calculate the pH, POH, and hydroxide concentration for a 0.0001 molar HCl solution. So the first thing to note is we just have to convert this into scientific notation. So what we do is we take the decimal point and we count the number of times that we move to the right. So we go 1, 2, 3, 4. Since we've moved it 4 times to the right, we can rewrite this as 1 times 10 to the negative 4, because we moved to the right 4 times. Consequently, if you move to the left, you would just change this to a positive for every one that you move to the left. But in these problems, you're going to be always moving to the right, because it would be less than 1. So we move to the right 4 times, we get a negative 4. Now, you can tell me what the pH is then from this. We just take the negative of this number, and we get 4. And then you can tell me the POH, because all you have to do is what's 4 plus what number gets us to 14? And so you'll tell me 10. And then to get to the OH concentration, you're just going to, again, use this number and make it 1 times 10 to that number negative, right? Or look back up at the H3O concentration, just say it's going to have to be 10 to the negative 10, right? Piece of cake, right? You guys have no problem with this. You could also do these in this order instead, but same answers. Okay, what is the OH concentration if the H3O plus concentration is 1 times 10 to the negative 8? Again, we're just looking, what does it have to add up to get to negative 14? It's going to be a negative 6, right? 1 times 10 to the negative 6. What is the pH if OH concentration is 1 times 10 to the negative 10? So note here, OH concentration is this, but we want the pH. So this is one of those tricky ones. You have to do an additional step. So if this is the hydroxide concentration, the H3O plus concentration is going to be 1 times 10 to the, remember we have to ask, what does this, to get from this to negative 14, we need an additional negative 4. And then the pH is just always this number made positive if this is just a 1. So it's just going to be 4, which is number 2 there. Okay, if we have a 0.1 molar hydrochloric acid solution, it has a hydronium ion concentration of 1 times 10 to the negative 1 moles per liter. Calculate the pH, a hydroxide ion concentration, and the POH for the solution. So note here, we have, again, base 1. It's 1 times 10 to the negative 1. So pH is just going to be this number made negative, 1. Which means the POH is just that, whatever it takes to get up to 14 from that, which would be 13. And then the concentration is just going to be of OH. It's going to be 1 times 10 to the negative. Again, it's this number plus another negative number to make negative 14. It'll be negative 13, right? So here's the solution. We find the pH. Just take the negative log of it. We get 1. And then next we find the POH. 14 minus the pH is 13. And then the hydroxide ion concentration can be calculated from the POH by taking 10 to the negative that, which is just 10 to the negative 13, so 1 times 10 to the negative 13 molar. Okay, now in all those other examples, we've always had base 1. What happens if I give you a base that's different than 1? So here we have a sulfuric acid solution, has a hydronium ion concentration of 3.2 times 10 to the negative second. So how do we go about answering this if we're trying to calculate the pH, the OH concentration, and the POH? So the pH can be found first. We just take the negative log of that number. Again, just put this in your calculator. And you'll get a negative 1.5, which becomes 1.5. By the way, all of your pH and POH numbers, you'll know you have right if it's a positive. At least you'll know you're on the right track if it's a positive number. If you get a negative number, you did something wrong. Most likely, you just forgot to take the negative of the negative. Now, if that's the pH, and the POH is always just going to be 14 minus that, which leaves us with 12.5. And then, to find the concentration of OH, we just use our calculator. You use the 10 to the x number. So you'll punch in the number. In this case, it would be a negative 12.5. And then you'll hit the 10 to the x key. Or if you have a graphing calculator, you would just write 10 and then caret, and then you go negative 12.5. And when you do that, you'll get a number 3.2 times 10 to the negative 13. So you're just putting these in the calculator and getting them that way. Okay, now strong acids lose their hydrogen ions easily and completely. Example is hydrochloric acid. It easily and completely will lose that hydrogen ion. Strong bases lose their hydroxide ions easily and completely. A good example is sodium hydroxide. Weak acids and bases do not ionize completely. Good examples of this being like boric acid, or here calcium hydroxide. So a strong acid, HCl, can be concentrated, like 10 molar, or can be diluted, like 0.05 molar. The same is true for strong bases and weak bases and acids and bases. The stronger the acid, the higher the acid ionization constant. The stronger the base, the higher the base ionization constant. Note here in this case, there's an ionization constant for water. We just call it Kw. But on each different acid and each different base, there's a different ionization constant. And they're different depending on if the acid or base is strong or weak. Well, here's a question. Are all concentrated acids strong? True or false? All concentrated acids are strong. The answer is false. You can have weak acids that are concentrated, and you can have strong acids that are diluted. Now, an amphoteric substance is a substance that can be either an acid or a base depending on conditions, and a great example of this is water. Water can serve as an acid or a base depending on conditions that it's interacting with. It acts the opposite of the substance to which it's exposed. So if if water is exposed to a strong acid, water will act like a base. And if water is exposed to a strong base, it will act like an acid. Now, a monoprotic acid is something that can give one hydrogen ion. A good example of this is HCl, hydrochloric acid. A diprotic acid is one that can give two hydrogen ions, like this, carbonic acid. Or triprotic is something which you can give three hydrogen ions, like this, phosphoric acid, H3PO4. Both diprotic and triprotic acids are generally called polyprotic because they can give more than one hydrogen ion. Polyprotic acids have smaller Kas as they lose successive protons. They become more negatively charged, thus it becomes harder to lose more positive protons. True or false? HNO3 is a triprotic acid. This question is trying to throw you off because you see that NO3 and that 3 is right there, but note that that's not attached to the hydrogen, so that's false. Here, this is just a monoprotic acid. It just has one hydrogen plus ion to give. Okay, now when it comes to indicators, indicators change color when pH changes. They give a rough estimate of pH, and that's what we were talking about litmus paper before with acids and bases. It's not as exact as a pH meter, which will just give you like a value, which are more recent developments. But pH indicators have been used for many years to give a rough estimate of the pH of various solutions. A universal indicator is a combination of indicators used to show a wide range of color changes over the 0 to 14 pH scale. And there's transition intervals where a range of pH values over which the color change occurs. So here's some examples of various materials that you can add that will provide a different color change at different areas. So you have methyl violet, thymol blue, bromophol blue, methyl orange. You notice that all of those guys are on the acidic part of the chart. Then litmus, methyl red, bromophol blue are all ones, and even thymol blue, even though this is on the base side, you see that it comes close to neutral, but especially these three in the middle are ones right there at the transition. Remember, 7 is the place at which neutralization. And then thymol blue, phenolphthalein, and alizarin yellow red are all here on the base side of the scale. And so these color changes happen over this pH range. So if you had something that you were moving from one place to the other through adding an acid or adding a base, you would see these color changes happen as you travel through that pH range. Here's some color changes as a function of pH for red apple skin, beets, blueberries. Red cabbage is particularly great at this. And if you have access to red cabbage or your parents buy some, all you have to do is take some red cabbage and boil it in water for a while, and then take the resulting juice from that and put it into a glass or something. And if you add something acidic or add something basic, you can get brilliant color change, all the way from really red when it's acidic, going through a kind of a purple violet, blue, and then into green as it becomes more and more basic. So, and then it even becomes yellow up here when you get above a pH of 12. And here's just a few more of those to look at. All right, which brings us to section C, a quick discussion of neutralization. So a neutralization reaction happens whenever you take an acid and you add it to a base, and it yields a salt and water. And I already kind of shown you an example of an equation like that, but the H plus of the acid combines with the OH of the base to make HOH, which is then your water group, right? Hydrogen plus hydroxide, H2O, which gives us water, which is neutral. Salt means whatever is left of the acid and whatever is left of the base. So whatever is left from the acid after the H plus goes away, whatever is left of the base after the OH minus goes away, those things come together to form the salt. And then the H and the OH combine together in this double replacement reaction to form water. Example, HCl plus NaOH yields HOH or H2O plus NaCl, salt or table salt, sodium chloride. Now there are 3 basic types of salts. You have acidic salts, basic salts, and neutral salts. When the acid and base are mixed, the stronger one determines the type of salt that is produced. So if you have a stronger acid combined with a weaker base, it's going to be an acidic salt. If the base is stronger than the acid, it's going to be a basic salt. And if the strengths of both acid and base are relatively the same, you're going to form a neutral salt. Now, what do acids neutralize? Acids neutralize bases, right? Acids neutralize bases, and bases neutralize acids. So sample problem number 1, write a neutralization reaction to produce zinc chloride a salt. So the question here is, what is it that comes together to form zinc chloride and water? If it's a neutralization reaction, what comes together to form that? So first of all, we were provided already that we have zinc chloride, which zinc is, remember, a +2 on the periodic table. We can note that. It's on the second column. It's an alkaline earth metal. And then we have chlorine, which is a halogen. It's a -1. So this +2 is balanced by 2 chlorine atoms. We have zinc chloride, and then +2 H2O. So the question is, what is it that's coming together to form both this salt and water? And we can kind of work backwards here. Salts are made from the anions of acids and the cations of bases. In this case, the most common acid that releases chlorine ion is hydrochloric acid. So 2HCl. Zinc hydroxide is a likely source for the zinc ion, ZnOH2. Now note here, hydrogen is a +1, chlorine's a -1, so that was fine. Remember, zinc is a +2. The hydroxide group is a -1, so we needed to write the parentheses with a 2 here to balance that compound. And then when you look at the entire equation, you note that you have to add a 2 here and a 2 here in order to balance the entire equation. What about this one? What salt is produced from the neutralization of barium hydroxide by acetic acid? So we're given acetic acid because it's maybe one that we don't know as quickly, but barium hydroxide you should be able to figure out. Barium hydroxide would be barium, Ba. Hydroxide is that OH-, right? And in this case, remember, barium is a +2, whereas this is a OH is just -1. So we need 2 of the OH groups. So we write that down here. Here's our acetic acid. Here's our barium hydroxide. We're yielding water. The question is, what is the salt that's produced? Well, we look at the part of the base that's not hydroxide, and we look at the part of the acid that is not hydrogen, and we put them together. The barium here is the plus, right? This is the +2. And here we have the -1. So when we get together, we have barium and acetate. We have barium acetate. And note, we have to put the parentheses around this whole thing and put a 2 here because, remember, barium is a +2, and this whole thing is a -1. So we need 2 of those. And then, again, these coefficients come in because we have to balance everything on the left with everything on the right. Okay, now a titration is whenever we're going about the actual experimental apparatus to determine the relative pH of a substance. So we can determine the unknown concentration of a solution by measuring its capacity to react with a solution of a known concentration. This is when we mix acids and bases to determine the pH, the concentration of either the acid or the base by using an acid or a base that we know. And then we can solve for the one that we don't know by knowing the amount of volume that we need in order to balance the two out or to neutralize. So a graph that shows the pH change when you would add an acid or a base or an acid to a base or a base to an acid is called a titration. And it looks something like this. So in this case, if we have sodium hydroxide and we start adding hydrochloric acid, over time, this has become less and less basic and become, at some point, come to a place of pH 7, neutralize it. But then if we keep adding the acid, it'll start to become more and more acidic. There's an equivalence point. Now, we can also go the other way. If we have something that has a very acidic pH, close to 0, and we begin adding more and more sodium hydroxide, in case a strong base, we'll start to raise the pH until eventually we get again to that neutralization point at around 7. If we keep adding that base, eventually it'll start to become more and more basic. This is just showing a couple of indicators that we could have in the solution such that we can watch the color change. So we'll know as we go through, if we have bromoscope green in here, as it goes from yellow to green to blue, we know we're getting closer and closer to 7. If we had phenolphthalein, everything's going to be kind of clear until it starts to become a base when it starts to turn more and more pink. Equivalence point would be found in between there. So on a titration curve, the equivalence point is the point at which there are equal amounts of acid and base, a pH of 7. The end point is the point at which a titration is stopped once the indicator changes color. That's when you know to stop adding the acid or base, because the color change is not indicated. We've gotten to the point that we needed to get to. So why would you do a titration? It's to find the concentration, right? You're trying to find the concentration of an unknown substance by use of a known concentration. And the way the calculation works is actually quite simple. You take the molarity of the known substance. Remember, you have a molarity that you don't know that you're trying to solve for, but then you have a known amount of volume. You take a certain amount of volume of the unknown, whatever, you pick whatever number you want, but you put a volume of that in a flask, and then you start adding a volume of the known molarity until you get that color change. And once you do, you stop, and you then calculate how much of this did I put in. And then you already know what you originally started with the volume of the unknown thing. And then you can solve for this one unknown through the things that you know. You know the molarity of the known solution. You know the volume of that known solution. And you know the volume of the unknown solution. You just don't know its molarity. And so you can solve for this. Here's an example problem. If you have 52.7 milliliters of a 2.13 molar hydrochloric acid solution, and it's titrated with 76.9 milliliters of a sodium hydroxide solution, what is the concentration of sodium hydroxide, of NaOH? So we have a known amount of a known solution, and we now have utilized this amount of the unknown solution. And we're looking for the concentration of this. So we just take the volume of the first one times the molarity of the first one, and then divide by the volume of the second one to give us the molarity of the second one. Looks like this. Molarity of the known times the volume of the known equals the molarity of the unknown times the volume of the unknown. So we knew this molarity, we knew the volume that we had of that. We then know the volume of the unknown molarity, but we just don't know its molarity. So now we're just going to divide by this number over to here, which ends up equaling 1.46 molar. Here's another example of 24.9 milliliters of a 1.34 molar hydrochloric acid is titrated with 17.8 milliliters. What's the concentration of NaOH? Now, by the way, without even doing the math, we can probably do a quick check of this. So we're going to take this number, multiply it by this one, and then we're going to divide by this one. So let's just compare the difference between this guy and this guy. So this is roughly what? It's not quite half, but around half as much. So it took less of this guy in order to equalize a little bit more of this one. So we're looking for a number probably that's going to be greater than this one, right? But probably not this much greater. Certainly not this much less. So the only ones that even make any ballpark sense are either 1 or 4. But note, if this number is smaller, it needs a bigger number multiplied by it in order to equal this bigger number times this number. So we could probably make a hazard a guess that it's this answer without even doing the math. But let's do the math now on the next slide. Just look at it. So again, we just plug in the numbers. We knew this volume, we multiply it by that molarity, and then this is the molarity, or I'm sorry, the volume of the unknown molarity. We're just going to divide by this number. We multiply these two together and then divide by this one. And we get 1.87, which was the answer on the previous slide. How much 4.56 molar HCl is used if it's titrated with 37.9 of a 2.18 molar solution? So in this case, we know the molarity of both, and just asking how many milliliters are we going to need of this one in order to balance this out. So notice that the molarity of the other one is like double the molarity of this. So it's probably going to be around half the amount of volume that we need to balance this. So I could just hazard a guess right off the bat that it's probably this one. But let's do the math again. Or maybe I already solved it. You can do the math on the previous slide. All right. So a volume of 108 milliliters of 5 times 10 to the negative 3 can neutralize 36 milliliters of nitric acid solution. What's the concentration of nitric acid? So here we have a volume, we have a molarity. So we're going to multiply those together and divide by this volume, and we'll get the concentration. So again, we take the molarity of the known times the volume of the known and divide by the molarity or the volume of the unknown. This should be volume, not molarity. Volume of the unknown should be down here, which is what's written down here. So you just do that math. 5 times 10 to the negative 3 times 108, divide by 36, and you get a 0.015 molar solution. All right, two last slides to mention. Buffers. So these help keep the pH fairly constant, not necessarily neutral, when small amounts of acid and base are added. They consist of a weak acid and its conjugate base, or the opposite combination. The weak acid neutralizes a base when it's added, and the conjugate base neutralizes an added acid. So weak acids and weak bases just prevent pH from moving too quickly whenever an acid or base is introduced to the system. Well, that's a quick overview of the chapter. Encourage you guys to go ahead and read through the chapter, do the ending of each section review problems. I'm not assigning the end of chapter reviews to you right now, so it's a little bit less work for you guys to have to do. So you're just doing sections A, B, and C, the end of each section little review. And I posted those answers also online for you, so you can check your own answers. But let me know if you have any questions. Hopefully this stuff is coming together. Read through the chapter. If you need to, watch this video again. Rewind on the parts that were a little bit tricky maybe. And let me know if I can help you in any other way. Love you guys. I'll see you soon. Stay safe. Bye-bye.